Imagine trying to create an immersive 360-degree experience from just a single phone photo or video clip. Most methods today require precise camera calibration data that simply doesn't exist for everyday content. Today we're exploring a breakthrough approach called 360Anything that eliminates this geometry dependency entirely. Let's start by understanding why this geometric dependency has been such a roadblock. Building on this challenge, existing perspective-to-panorama methods rely heavily on pixel-aligned conditioning that projects the input view onto the 360-degree canvas using known camera parameters. When this metadata is missing or inaccurate, the entire pipeline becomes unreliable, severely limiting real-world applications. The authors propose a fundamentally different approach that sidesteps geometry entirely. Instead of relying on geometric projections, the researchers treat both the input perspective view and target panorama as sequences of tokens. By concatenating these sequences and using transformer self-attention, the model learns to understand spatial relationships and placement directly from data, completely bypassing the need for explicit camera parameters. The OmniDiT architecture builds on pre-trained diffusion transformers like Flux for images and 1-2 for videos. The key insight is the canonicalization process that creates gravity-aligned training targets, forcing the model to learn proper spatial placement regardless of input camera orientation. Now let's examine the technical breakthrough that makes seamless 360-degree content possible. A critical technical contribution addresses the persistent scene problem in 360-degree content. The authors discovered that zero pairing in VAE encoders creates latent discontinuities at panorama boundaries. Their circular latent encoding solution applies circular padding before encoding, then removes the padded tokens, ensuring seamless wraparound without computational overhead. This visualization demonstrates the dramatic improvement in scene quality. While traditional approaches and even blended decoding methods still show visible artifacts at the panorama boundaries, circular latent encoding produces truly seamless results that are essential for immersive viewing experiences. This comparison highlights the fundamental paradigm shift. Traditional geometric methods create a rigid pipeline that breaks when assumptions fail, while the token-based approach provides flexibility and robustness by learning spatial relationships directly from data without geometric constraints. The training methodology reveals how the authors achieve this geometry-free capability. The training strategy centers on creating canonical, gravity-aligned panoramas that serve as consistent targets. By using both simulated and real-world camera trajectories during training, the model learns to handle diverse input conditions while always producing properly oriented 360-degree content. The canonicalization process is crucial for training stability. Raw 360-degree videos often have arbitrary orientations and fluctuating horizons, making it difficult for the model to learn consistent spatial relationships. The two-stage pipeline first stabilizes camera motion, then aligns gravity with the vertical axis, creating clean training targets. Let's examine how this approach performs across multiple evaluation scenarios. The quantitative results demonstrate clear advantages across standard evaluation metrics, with particularly strong performance in panorama-specific measures like FAED. The model shows robust generalization, successfully processing diverse content including AI-generated images that weren't part of the training distribution. Video results show consistent improvements across both fidelity and perceptual quality measures. The model maintains temporal coherence while generating high-resolution panoramic video sequences, though current computational constraints limit context to 81 frames. These qualitative results showcase the model's versatility across different scene types and input conditions. Notice how the generated panoramas maintain visual consistency while plausibly extending the scene in all directions, creating immersive experiences from single perspective views. Perhaps most remarkably, the model develops an implicit understanding of camera parameters, despite never being explicitly trained for this task. When evaluated on standard camera estimation benchmarks, it performs competitively with supervised methods, demonstrating that spatial reasoning emerges naturally from the token-based training. The generated content proves valuable for downstream 3D applications. This demonstrates the practical 3D reconstruction pipeline enabled by OmniDiT. Starting from a monocular input video, The model generates panoramic sequences with sufficient 3D consistency to support Gaussian splatting optimization, creating explorable 3D environments from limited input data. The 3D reconstruction results validate that the generated panoramas maintain geometric consistency sufficient for structure from motion algorithms. This enables practical applications in virtual environment creation and immersive content production from minimal input data. Let's acknowledge the current constraints and future research directions. The authors honestly acknowledge current limitations, primarily stemming from computational constraints and the inherent biases in pre-trained foundation models. The high resolution of equirectangular panoramas creates memory bottlenecks that limit video sequence length, while complex physical phenomena remain challenging to model accurately. 360Anything represents a paradigm shift from geometry-dependent to geometry-free 360-degree content generation, opening new possibilities for immersive experiences from everyday perspective content. To explore more cutting-edge research like this, visit emergentmind.com, where artificial intelligence meets human curiosity.